Good morning, students. Today we will discuss some further properties of inner product spaces. So the first property is squash inequality. If we take an inner product space X, then in that space for every two elements X and Y, we have inner product of X with Y mod that is less than or equal to X norm into Y norm. This inequality is called squash inequality. In particular case, we have the equality sign holds if and only if the set formed by the elements X and Y is linearly dependent set. So first of all, we prove the inequality. So first we take the case if the element Y is 0. If the element Y is 0, in that case the inner product of X with Y, that will become inner product of X with 0. So that is 0. So in this case the squash inequality holds trivially. Now let us consider the another case when the element Y is not equal to 0. Now for every scalar alpha, let us consider X minus alpha Y norm square. Now by definition of norm is given by the square root of inner product of the element with itself. So X minus alpha Y norm square means inner product of X minus alpha Y with itself. Now by using the properties of inner product, this will become inner product of X with X plus inner product of minus alpha Y with X plus inner product of X with minus alpha Y plus inner product of minus alpha Y with minus alpha Y. Now by using the property of conjugate linearity in the inner product spaces, this will further become inner product of X with X minus alpha into inner product of Y with X minus alpha conjugate into inner product of X with Y plus alpha into alpha conjugate inner product of Y with Y. Now combining the terms which contains the scalar alpha, and in particular if we choose alpha bar as the element inner product of Y with X divided by inner product of Y with Y, in that case we can see that the expression inside the brackets that becomes 0. So in this case the inner product of X with alpha Y norm square, that becomes inner product of X with X minus alpha bar into inner product of X with Y. Now substituting the value of alpha bar here, alpha bar is inner product of Y with X divided by inner product of Y with Y. Now inner product of Y with X, this is inner product of X with Y conjugate. Now using the properties Z into Z bar, that is Z mod square. So from here we get X minus alpha Y norm square is equal to X norm square minus inner product of X with Y mod square divided by Y norm square. Now because norm is non-negative, so this expression that will be greater than or equal to 0. So from here we get X norm square into Y norm square minus inner product of X with Y mod square is non-negative. Now taking positive square root, we get inner product of X with Y mod is less than or equal to X norm into Y norm. So this inequality is called squash inequality. Now we'll consider the particular case, the case in which the equality sign holds. Now we can see that the equality sign holds if and only if Y is 0 or X minus alpha Y norm square is 0. Now norm is 0 if and only if the element itself is 0. So from here we get X minus alpha Y is equal to 0. So from here we get X is some scalar multiple of Y, and if two elements are scalar multiple of each other or one of them can be written as a multiple of another, in that case the pair of the elements formed, that is linearly dependent. So we can say that the set formed by the elements X and Y is linearly dependent set. Thus we have proved that in the squash inequality, the equality sign holds if and only if the pair of the elements forms a linearly dependent set. Now next further property of inner product spaces is triangle inequality. In an inner product space X, For every two elements x and y, we have x plus y norm is less than or equal to x norm plus y norm. In the triangle inequality, the equality sign holds if and only if either the element y is 0 or x is some multiple of y with a scalar c that is real and non-negative. So first of all, we prove triangle inequality. So let us consider x plus y norm square. By definition of norm square, this is inner product of x plus y with x plus y. Using the properties of inner product, this can further be expanded as inner product of x with x plus inner product of x with y plus inner product of y with x plus inner product of y with y. Now, inner product of x with x, that is x norm square, and inner product of y with x, this is equal to inner product of x with y conjugate. Inner product of y with y, that is y norm square. Now, here we can use squares inequality and also the result that the absolute value of a complex number and the absolute value of its conjugate, they are always same. So we have the mod of inner product of x with y is same as the mod of the conjugate of inner product of x with y. Now we can use squares inequality for both of these. By using squares inequality, inner product of x with y mod is less than or equal to x norm into y norm, and also the same is true for the conjugate of inner product of x with y. So using two results here, this x plus y norm square is less than or equal to x norm square plus 2 times x norm into y norm plus y norm square. Now this expression is x norm plus y norm whole square. Now let us take positive square root on both sides. So we get x plus y norm is less than or equal to x norm plus y norm. So this proves triangle inequality. Now we'll discuss the case in which the equality sign holds. Now we can see from here that the equality sign here holds if and only if inner product of x with y plus inner product of x with y conjugate, that is equal to 2 times x norm into y norm. Now z plus z conjugate, that is 2 times real part of the complex number z. Here the complex number is inner product of x with y. So we can say that the equality sign holds if and only if 2 times real part of inner product of x with y is equal to 2 times x norm into y norm. Now 2 is cancelled out from both sides, so we can say that the equality holds if and only if the real part of inner product of x and y is equal to x norm into y norm. Now by squares inequality, this is further greater than or equal to inner product of x with y mod. Now because the real part of complex number cannot be greater than the absolute value, so therefore we must have equality sign here. So we get the real part of inner product of x with y is equal to the absolute value of the inner product of x with y. Now thus we can say that either y is 0 or x is equal to cy. So now it remains to prove that c is real and non-negative. Now to prove c is real and non-negative, we can see that we have equality sign in the triangle inequality if the real part of inner product of x with y is equal to the mod. But if the real part of complex number is equal to absolute value, in that case we must have imaginary part 0. Hence we can say that if the imaginary part is 0, it means inner product of x with y is equal to real part of inner product of x with y. But this is non-negative, so from here we get inner product of x with y is greater than equal to 0. Now x is cy, so putting the value here we get inner product of cy with y. Now c can be taken outside, so this will become c into inner product of y with y. This is y norm square because this is greater than equal to 0. So from here we get c is greater than or equal to 0. So this proves the properties of inner product spaces. Now next further property of inner product is that inner product is continuous function. So in order to prove this, we have inner product space X and we have two sequences Xn and Yn. Xn is a sequence which converges to X and Yn is a sequence which converges to Y. Then we are to prove that the inner product of Xn and Yn converges to the inner product of X with Y. So in order to prove this, let us consider the mod of the difference of inner product of X and Yn and inner product of X with Y. Now adding and subtracting the term inner product of Xn with Y here in this expression, and by using the properties of inner product, these two terms can be combined and these two terms can be combined. If we combine these two terms, this will become inner product of Xn with Yn minus Y, and combining these two terms, this will become inner product of Xn minus X with Y. Now by using the triangle inequality of real numbers, so this is less than or equal to mod of this number plus mod of this number. Now using the squares inequality, by squares inequality, inner product of X with Y is less than or equal to X norm into Y norm. So here these are the two numbers, so this will be less than or equal to norm of this into norm of this. In the same way here, using the squares inequality, this mod will be less than or equal to norm of this number into norm of this. Now because we are given that sequence Xn and Yn are convergent sequences, Xn is converging to X, it means Xn minus X approaches to 0 as n approaches to infinity. Also the sequence Yn converges to Y, means Yn minus Y approaches to 0 as n approaches to infinity. So from here we can say that Yn minus Y norm and Xn minus X norm, they are approaching to 0 as n approaches to infinity. Now this is approaching to 0, this is approaching to 0, this value is finite. Also the sequence Xn is convergent sequence, that is bounded sequence. So bounded means Xn norm, that is also finite. This is finite, this is approaching to 0, this is approaching to 0, and this is also finite. So we can say that this whole expression is approaching to 0 as n approaches to infinity. Thus we have proved that the mod of Xn Yn inner product minus the inner product of X with Y, this approaches to 0 as n approaches to infinity. Thus we can say that the inner product of Xn with Yn approaches to the inner product of X with Y. So this proves the continuity of the inner product. So these were the some properties of the inner product spaces.